Hello everyone, welcome back to your weekly therapy session. So today we have Christian Rosendal, and Christian is speaking on two applications of Arens-Eells space to geometric group theory and abstract harmonic analysis. Go ahead, Christian.
Okay, well, thanks for the invitation. So I'm gonna step a bit out of sort of the geometry of the Banach space mindset here and try instead to discuss sort of the uses of Arens-Eells spaces or Lipschitz free Banach spaces or whatever transportation cost spaces to other problems having to do with geometric group theory and sort of abstract harmonic analysis. So I'll try to, I'm giving a whiteboard talk, so I'll try to make it sort of simple and not too complicated, so we should all be able to follow. And I'll also try to give some proofs. So there are two applications I want to mention. One to geometric group theory, which is about coarse couplings of topological groups, of Polish groups, and the other is sort of a proof of a theorem by Friedrich Martin Schneider and Andreas Thom on characterizations of amenability for general topological groups, where I have a proof that uses Arens-Eells spaces, and sort of once you set it up, it becomes very elementary. Okay, so let me start by recalling what we're dealing with. Okay, so we'll start out with X a set. And then I'll define a few different objects associated with this. First of all, Rx, this is the vector space of finitely supported functions. So psi from X to R. And by delta of X, I'll denote the convex hull of the Dirac functionals. Okay, so you can think of Rx as simply being the formal linear combinations of points in X. So X is the basis, and the delta of X, this is just the convex hull of these basis vectors. Now also mx, what is that? That's the set of molecules. So this is the hyperplane in Rx of the psi of mean 0. Okay, so meaning that when you sum over its values, you get 0. Okay, so this is a hyperplane in Rx, and you can see that delta x here, this is a convex set in an affine subspace. In fact, it's a convex subset in a translate of M of x. Okay, so another way of writing this hyperplane is just you take the span of the differences by the Diracs. Okay, this is all well known. So let's okay, I can scroll up here. Okay, so observe that what? So if X is a group, then Rx is just a group algebra. Okay, so I mean, the direct functionals we can just identify with the points of x themselves, so we can write this instead as xi to be the sum of the ai xi. Okay, so it's just finite formal linear combination of the points, and then you get, so this is ai and
no problem.
Why this? No problem here. Okay, so with product, so you can multiply these. Okay, I think I prefer the other one, the Benjamin, the whiteboard. It's...
Okay, I don't know if you want to switch, but
Let me just finish it.
okay.
Okay, so you can multiply together finite linear sums, yeah, using the group operation, okay, and of course again you have if I take the formal the convex hull of the Diracs and I multiply it with itself, then I just get delta x. So delta x is a sub sort of it's closed on the multiplication in this in the group algebra. All right. So this is all abstract. Now, when do Arens-Eells spaces enter? Okay, this is so if D is a metric on X, then we get the Arens-Eells norm on mx, okay, on this hyperplane. Okay, so the Arens-Eells norms is just the transportation cost metric that we've seen several times. So this is the infimum over all expressions put absolute value here. Okay, so I write my my molecule psi as a linear combination of differences between Dirac meshes. Okay, and then I compute this infimum. So this is my the norm of my elements. Okay, now one thing about this is that you can compute this norm in a different way. So it's a, what is it? It's a cost of an optimal transport between the sources. So from manufacturers. So these are the set of axes where this is positive to consumers. Okay. But another way of saying, of computing this is by taking the supremum over the expressions here. Where f going from x to r is 1 Lipschitz. Okay, so these are the two ways of computing this norm. And because I'm really not, I'm interested in the way the norm is computed here, but I'm not interested in identifying the actual dual of the space. So I can just talk about 1 Lipschitz functions, but you can actually restrict various things. You can say, okay, you can always, we can assume that the AIs are positive. If they're not positive, we can always switch the order of xi and yi. And you can also assume that no x is both a manufacturer and a consumer. Okay, and you can also restrict to bounded Lipschitz functions. These psi, they all have finite support, so I don't really have to care about looking at all of f, so I can restrict it. And demands that that f takes a specific value at some point.
Excuse me, is that okay to interrupt with a question?
Yes, go ahead.
This infimum norm, would it stay the same if we omit multipliers modulus of AI?
What if you, well, I mean, you want, if you don't take them positive, then you could get a negative expression. So you don't want it.
But we
So
need,
you want
yeah, thank you.
To have a positive value. Okay, so so this last indication tells you that there are different ways of expressing the dual of this space here. When you complete mx with respect to the norm, then you get the dual, which you can either take to be the lib0 functions, those that are 0 at a specific value, or the bounded Lipschitz functions with the norm. Now, what you get from this is that, of course, I only have here, I have a Banach space, namely mx, under this norm. But I also have this other convex hull, which is not in a Banach space, but I can use the norm now to define a metric. Okay, so the norm here defines the Kantorovich metric. And this metric, of course, it makes sense on already delta of x. Okay? So delta of x is the convex hull of the the points in X. So the difference between two convex combinations of points in X will have mean 0, and therefore you get a metric on this space. Now, what's the use of the space? Well, so one indication is that so delta of X, this contains the Vietoris Rips complex of psi in this delta of X with the diameter d of the support of psi being bounded. Okay. Now, delta of X is a convex set. Okay, you can take convex combinations, but you can also make it complex, where you then so it's a simplicial complex, where you can simply by restricting to psi that always have a uniform bound on the diameter of the support. Okay? So this is a space being used in geometric group theory, and this will then be a subcomplex of this simplex X. Okay, so you can think of delta of X as sort of being the free convex space that contains X. Okay, so a few more observations are in place. Okay, so if I have a group that acts on X isometrically, so then that action naturally leads to an action of G on delta of X. Okay, I simply shift the support around using my group action G. Okay, and what is this group action? Well, this is an affine group action. It preserves convex combinations. And it's also an isometric action. And the embedding of X into delta of X, which takes point X and maps to delta X. This is a G so this is a G equivariant isometric embedding. Okay, so I start out from a group acting by isometries on some metric space X, and now I've made it act on this this convex hull of a metric space, or this free convex hull of a metric space in an affine way. So, well, what are the uses of it? Well, so let me see here. The problem with X is that there's no linear structure, there's no convex structure on it, whereas delta of X is sort of an object that's closely associated to it, and this Vietoris Rips complex lies inside of it, and which is even closer to X because it's consists of points with linear convex combinations with bounded supports. So what you can use it for, and I'll just sketch briefly here is that, so coarse embeddings of metric spaces of bounded geometry. I'll explain these words afterwards. Okay, so if I have a space Y and I have some embedding of Y into X, okay, and this is what we call a coarse embedding. So it's one that well, or you can have a sort of some discontinuous map that doesn't disturb the geometry too much. Right? It shouldn't be an isometric embedding, but just one which is well, if you think of Y as being a Banach space, maybe it's Lipschitz for large distances, and the inverse is Lipschitz for large distances. So this gives rise to a uniformly continuous coarse embedding of Y into delta things. Okay, so the idea is that once you are able to take convex combinations, you can often lift a badly continuous, a map which is not continuous in any way, but has some large scale, or it preserves the metric at a large scale, and you can replace it by a map that is now continuous, in fact uniformly continuous, and still has the same properties of preservation. So by augmenting your space to this convex hull, you can get improved mappings. So, okay, so what is bounded geometry? Bounded geometry is just to say that there is some diameter alpha, where such that balls of diameter alpha can uniformly cover balls of diameter beta for any beta. Okay, so we don't have to write down a precise definition, but it's just a natural restriction on metric spaces. So for example, so let me just write out a statement of the first application of these constructions. So this is that, so if I have two Polish groups, G and H, okay, of bounded geometry. So this is a Polish group is a topological group whose topology is Polish, so separable and completely metrizable. And bounded geometry, again, I won't go into the definition. So they are coarsely equivalent. Again, this is some discontinuous notion of preservation of geometry of the groups. And this happens if and only if they admit commuting continuous coarsely proper and modest actions on a locally compact space.
Christian Mikhail saying, do you mean bounded geometry or doubling?
Sorry? No, yeah, I want to say bounded geometry.
Okay.
Okay, I won't spend too much on time on the formulation here. I'll just, I think I can explain the motivation here. So you have, when you do nonlinear geometry of Banach spaces or geometric group theory, you end up with notions of equivalence between groups or Banach spaces, which involve discontinuous maps. Okay? So you have coarse equivalence or coarse by Lipschitz equivalence, or whatever you want to call it. And the problem is often to start from such a notion and replace that by something uniformly continuous or something continuous. And so the idea is that this space delta of x is a space which is close to x in some sense, in which you can replace these badly continuous maps by something which is uniformly continuous. So in this theorem here, you have this coarse equivalence between groups, which is just a map from G to H, preserving sort of the large scale geometry of G, but this will be in general very discontinuous. And now you're replacing that coarse equivalence by something where you have continuous actions on the same locally compact space. And so this is one instance where this delta of x comes up. But I want to focus on another example, which is where I can give a bit more details of a proof.
Christian.
Yeah.
Yeah. Maybe before you move to the next topic. So in the application here, it's not true if you don't have bounded geometry. Do you have like counter examples where?
Well, okay. So I want.
Or it's just for convenience.
You can. I think uniformly continuous is the problem here. So, for example, if you have a coarse embedding of one Banach space into the other, you can't in general replace that by uniformly continuous embedding, okay, which is close to the other one. So the bounded geometry is essential to preserve, to get uniform continuity.
Oh, okay.
So there's a paper by Now where he produces a coarse embedding of one Banach space into the other, which is not close to a uniformly continuous embedding.
Oh yeah. Okay. Yeah. Okay. Okay. All right. Thank you.
So that's where you use the bounded geometry. Okay. So let me go on to something where I can give you some more details. Okay. So this is about amenability of groups. Okay, so recall the following. So a topological group G is amenable if every continuous G flow, okay, so a continuous action of G on a compact space admits an invariant Borel probability measure. Okay, so G will preserve some probability measure on K. Now, there are oceans of reformulations of amenability. In particular, perhaps one of the most useful is that if G is locally compact, this can be reformulated as an isoperimetric, in terms of an isoperimetric criterion on the topological group itself. But there were no such criteria for more general topological groups. So, but so I'll prove the at least a part of the following result due to Schneider and Thom, which appeared a couple of years ago. Okay, so let's so let G be a topological group, and I'll simplify things a bit. And with a say a continuous right invariant, bounded metric D. Okay, so right invariance is just that GF HF, the distance between these two elements is the same as between G and H. Okay, so then the following are equivalent. Okay, so the so G is amenable, and then we'll find the appropriate sort of isoperimetric reformulation of amenability. Now, in Schneider and Thom's paper, this is not formulated in this way, and what I'm stating here is it contains the essentials of their formulation, but it's simplified by our language here. Okay, so for every finite subset, E and G. Okay, so the Filner criterion for a locally compact group says that whenever you take a finite subset of the group, you can find a compact set which is almost invariant under the actions of these finitely many elements. And that's formulated in terms of measure, in terms of the Haar measure on the group. Now, if you have a general topological group, there's no Haar measure. So you can't have such an isoperimetric criterion. So what we instead will talk about is the sort of the isoperimetric criterion in terms of the Arens-Eells norm. So so what you want is you want an element of delta of G which is almost invariant under all these finitely many elements. So recall that delta of G is a part of the group algebra. So I can multiply elements in delta of G. In particular, I can multiply them with the Dirac measures. So I think of G as being as being a direct measure. Okay, so I look at this beta, so it's a finite convex combination of points in G, and I want that that finite convex combination is almost invariant under the multiplication with the elements of G. And so this is this formulation, and we can also formulate this more explicitly. So so if G is non-discrete, or at least proof that applies to this case, is so for every finite subset E, there are finitely many elements of the group such that the maximum over G in G, and then infimum over permutations of N of the probability that d fi G f sigma I is less than epsilon, that probability is greater than 1 minus epsilon. Okay, so what
may I ask a question? Do you know if there is a nice reformulation of B and C if you replace A by G being extremely amenable?
yes, but it's a bit complex. I mean, you have to multiply on the other side of with G here. So okay, it gets a bit complicated, but there's a reformulation, but essentially it doesn't differ from the reformulation which is already in Pestav's book. So this is it doesn't really give you anything new. This criterion doesn't give you anything new for extreme amenability. So it's just a criterion that you can find in Pestav's books.
Okay, thank you.
Okay, so for amenability, so let's look at the last case here is simply that my beta here, I can write it as the average of a finite sequence, namely this finite sequence here, and then you can reformulate things a bit and just say that for every G, you can find some permutation of the numbers from 1 to n, so that Fi is close to G F sigma I with a great probability when you use the uniform probability on n.
Christian, I'm sorry, I must be missing something obvious. I don't understand what probability means here. What is a random?
I'd say it's the uniform. Sorry, I should be explicit. It's the uniform probability on the numbers 1 through n. Okay, so
thank you.
The proportion of i's so that the distance here is less than epsilon is greater than.
Okay, thank you. It's very clear. Thank you.
That's all. So it's really the first, as you can see here, the Arens-Eells norm now permits us a reformulation here of amenability as an isoperimetric inequality. Okay, and so this is, I'll try to give the proof here, which is surprisingly easy and which is really an indication of the utility of Arens-Eells spaces in a more general setting than just geometry. Okay, so let's focus on A implying B. Okay, so what is this statement? Okay, so we associate a Banach space to this, namely I take X to be the direct sum of, so I start with an amenable group, I have my finite subset E here, and now I take the direct sum of E copies of my the Arens-Eells space MG. Okay. Okay. And then I define a convex set C in X. So this is what? So it's just the set of G beta minus beta for G in E, where beta is an element of delta of G. Okay. So we can see the statement now. So what I'm saying is, so B can be reformulated in terms of this set C. So B simply says that what? That 0 is an element of the convex hull, of the closure of C. Okay? That I can approximate 0 using these beta and delta of G. And C is convex simply because I'm choosing my betas in delta of G, which is a convex set. Okay, so so that's the goal that we have to aim for. Okay, so now what are the tools? So I won't be using the above formulation of amenability, but I'll use a slightly different one. Okay, so I consider the algebra okay, so this is the algebra of so uniformly continuous of so bounded uniformly continuous sorry, I want so maps from GD to R. We'll use phi as a generic name for these. Okay, so this is the algebra of such functions. Of course, the Lipschitz functions is a subclass of this algebra. And so what is amenability? So amenability says that so there is a mean M on this algebra. Okay, so normalized positive linear functional on this algebra of functions, which is invariant under the left regular representation. Okay, so L, so this G acts on this algebra. Okay, the left regular representation of G acts on the algebra of right uniformly continuous bounded functions, namely, so L G phi, this is just a phi precomposed with multiplication here by G inverse. Okay. So my goal is to show that this set C here contains the point 0. Okay. And I'll use the left regular representation in my mean here. And so now the argument becomes extremely simple. Okay, so, well, what happens if 0 does not belong to a closed convex set? Well, you just use Banach. So then, by Banach, there is a linear functional. Okay, so this is in. So let's write out what this is. So this is it's a sequence of linear functionals, really. Okay, so we call X here, this is the direct sum of E copies of M of G. Okay. And this functional separating 0 from C. Okay, so with the infimum over X in C of phi of X being strictly positive. Okay, so that is what I have. I've separated my set C from 0 using this linear functional. Okay, so now we know what the dual of these spaces MG are. Well, they are they're Lipschitz spaces. Okay, so now each phi G in MG here star defines a Lipschitz function in the usual way, namely it defines a Lipschitz function on G simply by evaluating phi of G on the difference between delta F and delta at the identity. So the Dirac functionals as at F and the identity. Okay. So, so what does this mean? Well, I have a sequence of them, E many of them, and that means that I can define a right uniformly continuous function here. Okay, so this function here, so I take these Lipschitz functions, yeah, they will be right uniformly continuous because my metric is right invariant. And therefore, when I take, I can act on them by the left regular representation, and I can take the difference, and I can take the sum. This will all lie in my algebra of right uniformly continuous bounded functions on G. Okay. Now, let's look at this function here. So clearly, if I look at my mean, so remember my mean, this was an invariant functional on this algebra of right uniformly continuous function, so I can evaluate it. Yeah. Well, if you write it out, this is of course just m of L G inverse phi G minus m of phi G, yeah. And by by invariance on the left regular representation, these elements, they don't do anything to my value of m. So this is all just a difference of two identical points. So this is just 0. Okay. So on the one hand, my mean says that this function is trivial. Okay. But I'll show that this function, by assumption, is actually positive. So this is by L invariance of M. But if you look at phi, C evaluated at the point F of my group, this is just the sum over my set E, and you can rewrite it easily to get phi of delta GF minus delta F, and this will just be capital phi of G delta F minus delta F over E, okay? Which is an element. This here is an element of C. Okay? So this will be at least rho, which is positive. So this so then C is a bounded right uniformly continuous function, and this will be a positive function, okay, on which m, which is a mean, takes the value 0. So this is a contradiction. So this contradicts the positivity of my mean m. Okay. So this shows that zero really is it's a limit point of my convex set C. Okay, I'm out of time here, I can see, so I'll stop here. Actually, this criterion itself, this can be used for proving things about Banach spaces, but I won't have time to go into this.
Okay, thank you so much. We can take questions or comments.
excuse me. My question is about what I wanted to know. Is there any relation between Schwartz space, like the space of test functions, and LP functions, which are Lipschitz of some order, let's say alpha? Thank you.
I wouldn't know. I wouldn't be the right person to ask questions.
Thanks.
I have a question about the coarse coupling theorem you talked about.
Yeah.
Can you say a little more about it? The proof of the coarse. How does it work if they have a commuting coarse action?
Well, so this direction here is rather easy.
Yeah.
It's the other direction which is difficult. Okay, so the difficulty lies in from some coarse data, which is this very discontinuous map, to arrive at something which produces continuous actions on the same space. So that you really need you need to start with a very discontinuous map and replace it by something which is uniformly continuous. Okay, so this is well known in as a problem in linearizing or general maps, that you need that this replacement of coarse maps by uniformly continuous maps is non-trivial. So the proof here is long, and there are several elements going into it. So it'll be a bit difficult to explain what exactly is needed here. But the main thing is this application here, that you take a general map and replace it by a map which is now uniformly continuous and which doesn't alter the original map too much, which is close in some sense to the original map you started out with.
Okay, thank you.
Thank you. Anybody wants to jump in?
So can you say more about the applications that you didn't have time to?
Okay, yes, I can. Okay, so maybe I'll state one thing here. Okay, so of the Schneider-Thom theorem, you don't need exactly this formulation, but you can. One thing I proved using amenability is the following statement. Okay, so suppose X is a Banach space. Uniformly embeddable into B of E for a super reflexive space. E. Okay. So I have a Banach space which is uniformly embeddable. So there's a uniform embedding into the ball of a super reflexive space E. So then X contains some little LP. Okay, now there are several things that there's a jump here between one theorem and the other. So let me say what's the idea here is that from amenability So if you take a Banach space, this is an amenable topological group. It's an abelian group, so it's amenable. So from this Banach space, if you have a uniform embedding into B of E, you can actually get X to act on a super-reflexive space by linear transformation, so by linear isometries. And then you can use this this action by linear isometries and combine it with results of Yves Reynaud regarding the analysis of superstable spaces, and then ultimately get this copy of little LP. So that's the idea. Is this is a part of a different project, is to sort of get Banach spaces to act on different Banach spaces, and therefore the amenability in whichever formulation you need, but this Schneider-Thom is particularly useful. Is useful for this criterion.
Christian, question about this theorem. For p bigger than 2, does LP uniformly embed into the unit ball of a super-reflexive space?
I don't know.
I think.
Wait, so let's see. This is in Moret, Mitiagin. There was a paper by Moret and Mitiagin, and who was the last person?
Aharoni.
Aharoni, yeah, from the mid-80s. So I don't remember what happens for p bigger than 2. Yeah, this is, don't worry about my notification, email notification.
Yeah, we can read your email. So you're saying that this condition implies X is stable? Is that what you're proving?
Yes, what you are getting is that, okay, let me. Okay,
I wish you presented this theorem rather than.
Okay, so maybe I should. Well, what you get is that. Okay, so the idea is that you get X. Since X is amenable, get an action, an isometric linear action. Of X on some E superstable, super reflexive. Okay, and it's an isometric linear action which actually will give you an embedding of X into the group of linear isometries of this super reflexive space. And so then it's what you get is that there is a stable metric, a stable invariant metric on X. So from this, and then you apply a result of Reynaud that says once you have a stable invariant metric, you get this copy of LP.
So here you need amenability of the whole space, right? Because in Reynaud's result, if I'm not mistaken, it just needs the uniform embeddability of the ball. But here it's not true, right? Because of Tyrrellson space.
No, you need the embeddability of the whole.
Yeah, you cannot replace by embeddability of the ball here. It's wrong, right? Yeah.
You need the invariant stable metric on X, and that you only get from this embedding into the geometry group of the space.
Oh, that's nice.
All right, thank you. Are there any other questions?
Yes, hello, this is Pedro. Thank you for the beautiful whiteboard lecture. I was wondering, coming back to this Schneider-Thom theorem, with an analog of this can be stated for Sophic or hyperlinear notions.
That's a good question. I haven't thought of that. I mean, there are of course reformulations of hyperlinear in terms of sort of some proximity in terms of metrics. I don't know.
I mean, I was looking to the appearance of the Arens-Eells space in particular, right?
Yeah. I haven't thought about that. That's a good idea. I mean, the main thing here is that once you set up these things with Arens-Eells spaces, all these notions become completely natural. There's nothing sophisticated about this proof. It's just you write it out and you apply it. But of course, the original proof was significantly more complicated. So it shows how these, well, I don't know if you should say, I don't know if it's the Arens-Eells spaces or just the concept of optimal transport, which is useful. Yeah. But once we have we understand these spaces well, that they can be used for many other things than just.
Okay, thanks.
Thank you. Any more questions? All right. If not, thank you so much, Christian, for a very nice talk. And so what we can do,